Right, in this video, I want to walk you really clearly step by step of how to calculate a torque given a force vector. And I'm going to do this using the force component-based method. I'll do a separate video for showing you other methods. So in this situation, we're going to imagine that you know what force vector is acting on an object, and you want to know what torque that force is exerting. All right, so I've given you a hypothetical example here that I've pre-drawn. We have like a rectangular object, like maybe we have this, and we exert a force on some point in the object that points down in some direction, and this might cause the object somehow to rotate, and it can rotate about its center point. So that X represents the axis of rotation. As I said, it's really important to note where the axis of rotation is located. And so this kind of gets us started. So step one is actually what I've already kind of pre-started here. You want to draw a free body diagram of the situation, which shows the force vector, including where it acts on the object. So it used to be good enough in the old days for us just to move all the force vectors to the center of the diagram and not worry about where they were actually located. Now it will actually be important where those vectors are located on the diagram. So which spot on the object is this force pushing on? So your diagram should include where the force is acting. So by that, I mean, for instance, in my diagram here, this is the point where the force is acting on the object, where I've placed that green circle. So that's the spot that's actually being pushed on. And you also want to include where the axis of rotation is located, which I've denoted with an X. I usually mark the axis of rotation as an X in my picture, or an X with a circle around it sometimes. Okay, so that's step one. Not surprisingly, you probably could have guessed what step one is, because this is step one of almost everything we do in the class. Get yourself a good picture so that you can actually see what's going on clearly. Okay, now what do we do? Step two, in my method, we want to draw a circle whose center is the axis of rotation and whose edge passes through where the force acts on the object. So in other words, in the picture that I'm drawing here, that circle would be something like this. Let me make a little bit of a smaller circle. About like that. So again, the two key features of this circle, the X, the axis of rotation, should be at the center of the circle. And this little green mark I made, which shows where the force is acting on the object, that should be on the perimeter of the circle. So this circle is basically the circle you're visualizing as being the possible rotation of the object as it goes back and forth. Okay? Now, third step, draw a line connecting the axis of rotation to the point where the force acts, and this will be a radius of the circle that you just drew. This is step three. Okay, so by this I mean we draw a line here from the X to where the force acts. So that line right there. The length of this line is what I was calling L. in the previous video. So the length of this line we are going to call L. So this guy is L. Okay. Now number 4, break the force into components. One parallel to that line and one perpendicular to that line. So in my picture here, remember when you break a force into components, you're always visualizing a right triangle. So basically one side of my triangle should be along the tangent to the circle, like that. And one side should be along the extension of L, like that. So for example, in this drawing here, the right triangle I visualize might be, let's get a color that stands out a bit more. So the right triangle I visualize would be something like here and here and here. And the right angle is, oops, the right angle is this corner here. Okay. Now, the side which is parallel to the tangent is what I call FT. So FT is this side. That's the one I'm interested in. The other side really doesn't matter. You can calculate it if you want to, but it really doesn't make much of a difference. Actually, the other side is basically related to the centripetal force that we learned about earlier, which is not really the focus of this section of the course. Let me write that here. The component perpendicular to that line, tangent to the circle that you drew in the earlier step, is what I am calling FT. Oops, got a little cut off there. Just rewrite that. Okay, so the component perpendicular to the line from step 3 and tangent to the circle from 2 is the component that I am looking for. Okay, that's the one that I'm looking for. That's the one that I am referring to as FT. Now, you take your L from this step and you take your FT from this step and you put them together and you multiply them. And the torque is FTL. The magnitude of the torque, anyway, is FTL. So it would be this length here times this side of this right triangle here. And that's what you want. And then you sign the torque positive or negative based on whether it's counterclockwise or clockwise. And that's the basic method. This may seem a little bit fiddly, but I like this method because I can see clearly that FT is the component that causes the rotation by this same argument that I've been making. We want the component that does this. We want to throw away the component that does this. And I can always remember which component I want because I can always think about it like, okay, like this or like this. And then when you sign the torque, by the way you know the sign of the torque is you just look at which way would the object rotate. Like say you released it from rest and this was the only force acting on the object, which way would it rotate? And so like if this force was the only force acting on the object, it would rotate this way, right? If you had, you know, pen and you push down on this side, it would rotate like that. So that is a clockwise rotation. So then this torque should be a negative torque. Clockwise is negative. So that's the way you get